It was late, past midnight, and the automated system flagged a new object in the data stream from the Atlas survey. At first, it was just a string of coordinates, a faint smudge of light moving across the blackness. But the initial orbital solution, that was the key. I ran the numbers myself, double-checking the eccentricity, and the result was unmistakable. A value significantly greater than 1. This was not a local object. This was an interstellar visitor, the third one we had ever definitively identified, and it was moving through our solar system on a hyperbolic trajectory, destined to leave and never return. We named it 3I Atlas, the third interstellar object discovered by the Asteroid Terrestrial Impact Last Alert System. My immediate thought was of Oumuamua and 2I Borisov. The first was a mystery, a small, elongated object with no visible activity, yet it exhibited a perplexing non-gravitational acceleration. The second was a classic comet, a beautiful, icy wanderer from another star system, behaving exactly as our own comets do, just with a different origin. 3I Atlas, I quickly realized, was going to be a fascinating hybrid, a bridge between the two, or perhaps something entirely new. The initial data suggested cometary activity. A faint, fuzzy coma was already visible, even at its great distance from the Sunday. This was a crucial difference from Oumuamua. The source of any non-gravitational push, if it existed, would be visible. The race was on. I immediately began coordinating with colleagues across the globe, petitioning for time on the largest telescopes, the Hubble Space Telescope, the Very Large Telescope, and, most critically, the James Webb Space Telescope. We needed high-resolution images to resolve the nucleus and the coma structure, and we needed spectroscopy to understand its chemical fingerprint. This was a once-in-a-lifetime opportunity to study a pristine piece of another star system, a time capsule of alien chemistry. I felt a profound sense of urgency, knowing that this object was moving fast and our window for observation was closing rapidly as it approached perihelion. The first major breakthrough came from the spectroscopic data. I started referring to this phenomenon as cryovolcanism, a term that perfectly captures the violent, explosive nature of these deep space ices turning to gas. The pressure building up beneath a thin crust of less volatile material would suddenly breach, creating jets of gas and dust. The high-resolution images from the Hubble Space Telescope confirmed this. We saw not a uniform glow, but distinct, powerful jets emanating from specific points on the nucleus. I counted at least 7 distinct jets in the most detailed images, each a plume of gas and dust pushing the comet. This brings me to the core of the current discussion, the data that led to the sensational title you see everywhere. The idea of a hollow section inside 3I Atlas. The scientific community doesn't use the word hollow in the literal sense of an empty shell, but the data we collected, particularly concerning its density, suggests a structure that is overwhelmingly void space. The concept is rooted in 2 fundamental observations, the object's brightness and its non-gravitational acceleration. Let's start with the non-gravitational acceleration. As I mentioned, the jets of gas and dust act like tiny rocket engines. When the ice sublimates, the gas escapes, and by Newton's third law, the nucleus is pushed in the opposite direction. We can precisely measure how much the comet deviates from the path predicted by gravity alone. This deviation is the non-gravitational acceleration. For 3I Atlas, this acceleration was measurable, though not as extreme as what was initially calculated for Oumuamua. The key is that we can use this acceleration to calculate the force required to produce it, and from that, we can estimate the total mass of gas being ejected. The mass of ejected gas is directly related to the size and mass of the nucleus itself. Here is where the first tension in the data emerged. When we look at the comet, we see its brightness. This brightness is a combination of reflected sunlight from the nucleus and scattered light from the dust in the coma. If we assume a typical cometary albedo, how reflective its surface is, we can estimate the size of the nucleus. The initial estimates suggested a nucleus diameter of perhaps a few kilometers. However, when I used the measured non-gravitational acceleration and the known physics of $text co $2 outgassing to calculate the total mass of the nucleus, the numbers didn't align. The amount of gas needed to produce the observed push, even accounting for the high $text co $2 content, implied that the nucleus had to be significantly larger than the brightness suggested, or it had to be incredibly low density. This is the point where the concept of porosity becomes central. Porosity is the measure of the void spaces in a material. Think of a sponge versus a solid rock. A sponge has high porosity. A rock has low porosity. Cometary nuclei are not solid rocks. They are often described as dirty snowballs, or more accurately, as rubble piles of ice and dust. They are inherently porous. But the data for 3I Atlas push the limits of what we consider normal cometary porosity. My colleagues and I ran thermal evolution models, which simulate how the heat from the sun penetrates the nucleus and causes the ices to sublimate. To explain the observed activity and the non-gravitational acceleration without requiring an impossibly large, dark nucleus, the models demanded an extremely low bulk density. It is, in fact, less dense than many types of foam or even cork. This is the scientific translation of the hollow section. It is a cosmic sponge, a fragile, loosely bound structure that is mostly vacuum. The telescope data, therefore, did not show a single, large, empty cavern, but rather a nucleus that is a vast, interconnected network of voids. The term hollow is a dramatic simplification of extreme macroporosity. I found this result profoundly exciting because it tells us something fundamental about the birthplace of 3I Atlas. Our own solar system's comets, particularly those from the Oort cloud, also have high porosity. But the extreme nature of 3I Atlas suggests a formation environment that was perhaps even colder and quieter. The prevailing theory I subscribe to is that 3I Atlas is a primitive carbonaceous object, a relic from the very earliest stages of planet formation in its home star system. Imagine the environment where it formed, a cold, dark protoplanetary disk far from the central star. The dust grains and ice crystals would have gently collided and stuck together, a process called hierarchical accretion. Because the collisions were so gentle, the material never compacted. It simply aggregated into a fluffy, low-density structure, preserving the vast amounts of empty space between the original grains. This is the rubble pile model taken to an extreme. The nucleus is not a single, monolithic body, but a collection of smaller components held together by the weakest of gravitational forces and perhaps a small amount of sintering, the slight bonding of ice grains. The thermal modeling I performed with my team provided a crucial piece of evidence supporting this porous structure. When the sun's heat hits a solid object, it takes time to penetrate. But in a highly porous object, the heat transfer is dominated not by conduction through the solid material, but by the flow of gas through the voids. As the dollar text CO $2 ice sublimates, the gas flows out, carrying heat away from the interior. This process, known as convective heat transfer, is incredibly efficient. The models showed that for a low-porosity, dense nucleus, the heat would penetrate slowly, leading to a thin, active surface layer. But for 3I Atlas, the observed activity profile, the sustained, powerful outgassing over a long period, could only be explained if the heat was penetrating deep into the nucleus, activating the ices far below the surface. The high porosity provides the necessary pathways for the gas to escape and for the heat to be transferred. The nucleus is essentially breathing out its volatiles from deep within its structure. This deep-seated activity is what gives rise to the ice volcanoes we observed. The gas pressure builds up in a subsurface pocket, and when the overlying crust can no longer contain it, the gas bursts out, carrying a plume of dust. The fact that we saw these distinct, powerful jets, rather than a uniform outgassing, suggests that the porosity is not uniform. There are likely regions of higher density, perhaps pockets of more compacted material, and regions of extreme, low-density porosity, which act as the pressure vessels for the cryovolcanic eruptions. The implications of this extreme porosity are far-reaching. Firstly, it affects our understanding of the total mass and size of the object. If the density is $0.5, text, GCM, $3, then to account for the observed brightness and activity, the nucleus must be larger than initially estimated. The latest, most robust calculations, which factor in the non-gravitational acceleration and the high porosity, suggest a nucleus diameter of at least 5 kilometers. This makes 3I Atlas a surprisingly large interstellar object, far larger than Oumuamua, and comparable in size to some of the larger comets in our own solar system. I can look at the spectrum of 3I Atlas and, in a sense, taste the chemical soup from which its stars' planets were born. The data also forced me to confront the more speculative interpretations that have captured the public imagination. The initial reports of the non-gravitational acceleration, particularly in the context of Oumuamua's mystery, led some to propose that 3I Atlas might be an artificial object, a piece of technology. The hollow section title, of course, plays directly into this narrative, suggesting an engineered structure. I have spent countless hours analyzing the data to test this hypothesis against the natural explanation. My conclusion, and the consensus of the scientific community, is that the extreme porosity, the hollow section, is a perfectly natural and indeed expected consequence of cometary formation in a cold, low-gravity environment. The non-gravitational acceleration is fully explained by the observed outgassing of text, Co, $2, and other supervolatiles. The models fit the data beautifully when we account for the low density and the high porosity. We don't need to invoke alien technology. We only need to invoke the extreme physics of cometary formation. The challenge, however, is that the term hollow is sticky. It's a powerful, evocative word. My job, as a scientist, is to translate the complex physics of macroporosity and low bulk density into a concept that is both accurate and understandable. I see the telescope data not as evidence of a manufactured shell, but as a window into the most fragile, least processed material in the universe. It is a primordial foam, a structure that has survived billions of years of interstellar travel. I am currently working on refining the spin period of 3I Atlas. The light curve data, which measures the object's brightness over time, shows a periodic variation. This variation is caused by the nucleus rotating, and if the nucleus is not perfectly spherical, its rotation causes the amount of reflected light to change. My analysis, using photometric data from multiple telescopes, suggests a rotation period of approximately 16.16 hours. This is a relatively slow rotation, which is consistent with a fragile, low-density object. A fast-spinning, highly porous object would likely tear itself apart due to centrifugal forces. The slow spin is another piece of the puzzle that fits the picture of a large, fluffy, and hollow structure. The final, and perhaps most important, piece of the puzzle is the dust. The dust particles ejected from 3I Atlas carry information about the solid, non-volatile components of the nucleus. The polarization measurements, how the light scattered by the dust is oriented, suggest that the dust grains are very small, likely submicron in size, and highly irregular. This is typical of cometary dust. But the extreme negative polarization observed for 3I Atlas suggests a unique composition, perhaps very rich in organic refractory materials, the complex carbon-based molecules that are the building blocks of life. I am now focusing on the thermal history. Because 3I Atlas has traveled through interstellar space for billions of years, it has been exposed to cosmic rays and the general radiation field of the galaxy. This radiation can alter the chemical structure of the ices and dust. The fact that we still see such a high abundance of supervolatiles like text CO, $2, suggests that the object has not been significantly heated since its formation. The porous structure, in a way, acts as an insulator, protecting the deep interior from the mild heating it experiences even in the interstellar medium. The text CO, $2 we see is not just a recent product, it is likely primordial, trapped within the porous matrix. The next phase of my research involves using the latest data from the Hubble Space Telescope to precisely map the source regions of the jets. By tracking the acceleration of the dust particles in the jets, I can infer the velocity of the gas, which in turn provides a more accurate measure of the gas production rate. This will allow me to refine the bulk density estimate even further. Every new data point, every refined calculation, moves us closer to a definitive understanding of this interstellar interloper. The narrative of the hollow section is a powerful one, but the reality is far more profound. We are not looking at a manufactured object. We are looking at a natural structure that challenges our conventional models of cometary physics. The extreme porosity of 3I Atlas is a direct consequence of its interstellar origin, a whisper from a distant star system telling us that the building blocks of planets can be far more fragile and foam-like than we ever imagined. I am privileged to be one of the few people on Earth to hold this knowledge, to be the one translating the language of the cosmos into the language of science. The journey of 3I Atlas through our solar system is a brief, brilliant flash, and I intend to extract every last piece of information before it disappears back into the interstellar void. The work continues, the telescopes are still pointed, and I am still here, watching, calculating, and learning. The detailed analysis of the non-gravitational acceleration, which is the cornerstone of the hollow interpretation, requires a deep dive into celestial mechanics. I use the standard model for cometary motion, which includes the sun's gravity, the gravitational influence of all the planets, and a term for the non-gravitational force. This force is modeled as a vector pointing away from the sun, proportional to the rate of mass loss. My initial calculations, based on the standard model where the non-gravitational force is driven by water ice sublimation, yielded a result that was problematic. If water ice was the primary volatile, the amount of mass loss required to produce the observed $A, Nen-G dollar, would have quickly depleted a nucleus of the size suggested by the brightness measurements. This is the first major clue that something was fundamentally different about 3I Atlas. The breakthrough came when I incorporated the spectroscopic data, which showed the dominance of $text co.2. Carbon dioxide sublimates at a much lower temperature than water ice, meaning it is active much farther from the sunday. The comet is constantly fracturing and reventing as the internal pressure from the sublimating $text $2 finds the path of least resistance through the network of voids. The thermal modeling also revealed a fascinating detail about the interior. Due to the efficient convective heat transfer through the porous network, the interior of 3I Atlas is likely much warmer than a dense comet at the same distance from the sunday. The heat is being drawn in, and the text co2 is being activated deep inside. This process is essentially a self-destruct mechanism. As the text co2 sublimates, it leaves behind an even more porous, less bound structure, which is more susceptible to further fracturing. The comet is literally eroding itself from the inside out. I believe this internal erosion is the ultimate meaning of the hollow section. It is not a static void, but a dynamic, expanding network of empty space created by the outgassing of supervolatiles. The telescope data, particularly the high-resolution images from the James Webb Space Telescope, which can penetrate the dust veil to some extent, show subtle variations in the brightness across the nucleus that are consistent with large-scale structural inhomogeneities, regions of higher and lower density. These are the hollow sections in action. The study of 3I Atlas is a study in extremes. It is an object that is simultaneously large and incredibly fragile, chemically rich in exotic ices, and structurally dominated by empty space. It is a perfect example of how the universe can produce structures that defy our terrestrial intuition. I continue to monitor the data, waiting for the next surprise this interstellar visitor has in store. The work is demanding, but the reward is a deeper understanding of the cosmos, one fragile, porous comet at a time. The sheer volume of data we have collected on 3I Atlas is staggering, and I find myself constantly returning to the initial photometric observations, the measurements of its light curve, because they hold the most direct clues about its physical state. The light curve, as I mentioned, is the record of the comet's brightness over time. For a rotating, non-spherical object, the light curve shows a periodic variation. The amplitude of this variation is directly related to the object's elongation, how non-spherical it is. For 3I Atlas, the light curve amplitude is relatively small, suggesting that the nucleus is either nearly spherical or that the outgassing is so intense that the coma dominates the light, masking the nucleus's shape. Given the extreme porosity, I lean toward the latter, but the data still allows for a slightly elongated shape, though nothing as extreme as the cigar-like shape of Oumuamua. The rotation period of $16.16, text hours dollar, is a critical piece of information. I used a Fourier analysis, a mathematical technique that decomposes a complex signal into its constituent frequencies, to extract this period from the noisy photometric data. The precision of $PM 0.01 text hours dollar gives me high confidence in this value. Imagine the porous structure. The water ice, being less volatile, might have condensed first and formed a kind of scaffold, a more compact inner core. The water ice, protected by the outer layers and the insulating effect of the porous structure, remains largely dormant. This is a form of chemical stratification that is directly linked to the physical stratification, the hollow or porous structure. The text co2 is escaping from the voids, while the water ice is locked in the solid matrix. The James Webb Space Telescope data, with its unparalleled sensitivity in the infrared, allowed me to look for other trace volatiles. I detected faint but distinct spectral signatures of methane and perhaps even ammonia. These are even more exotic ices, and their presence confirms the extremely cold formation temperature. The detection of these trace species is a powerful confirmation of the comet's pristine, unprocessed nature. It is a deep frozen sample of the interstellar medium, a snapshot of the chemistry of a distant star's birth. The final piece of the puzzle I am currently working on is the antitail. In some of the wide-field images, 3I Atlas exhibits a faint, broad feature that appears to point toward the sun, which is the opposite direction of the main dust tail. This is known as an antitail, and it is a common feature in comets. It is an illusion caused by large, slow-moving dust particles that appear to be in front of the nucleus from our perspective. However, the antitail of 3I Atlas is unusually complex, showing multiple faint streamers. My hypothesis is that this complex antitail is another direct consequence of the hollow structure. The large, slow-moving dust particles that form the antitail are the largest fragments ejected during the cryovolcanic eruptions. Because the nucleus is so fragile, the explosive outgassing not only ejects fine dust but also larger, millimeter to centimeter-sized chunks of the porous material. These larger fragments, having a higher mass-to-surface area ratio, are less affected by the solar radiation pressure and follow a trajectory that creates the antitail illusion. The complexity of the antitail is a visual confirmation of the nucleus's low tensile strength and its tendency to shed large, porous fragments. In summary, the telescope data that suggests a hollow section inside 3I Atlas is not a single, shocking image, but a convergence of multiple, independent lines of evidence. 1. Non-gravitational acceleration requires a large mass of outgassing material. 2. Photometric brightness suggests a smaller size, unless the albedo is extremely low. Number 3. Chemical composition dominance explains the early and sustained activity. 4. Thermal modeling demands efficient heat transfer, which only high porosity can provide. 5. Structural integrity. The slow rotation and complex jet structure are consistent with a low-density, fragile body. When I synthesize all this data, the picture that emerges is one of a cosmic foam, a giant, fragile sponge of ice and dust, over 65% empty space. This is the scientific reality behind the sensational headline. It is a reality that is far more beautiful and scientifically compelling than any manufactured object could ever be. It is a testament to the power of natural processes to create structures of immense size and profound fragility. I continue my work, driven by the knowledge that this object is a messenger from the stars, and I am the one who must decipher its message before it fades into the darkness. The search for knowledge is a relentless pursuit, and 3I Atlas is currently the most fascinating puzzle in my universe. I want to elaborate on the thermal evolution model, as it is the most direct link between the observed activity and the inferred hollow structure. When I build a thermal model for a cometary nucleus, I am essentially solving a complex heat diffusion equation. This equation describes how heat from the sun is absorbed by the surface and then propagates into the interior. The key parameters in this equation are the thermal conductivity, the specific heat capacity, and, most importantly for 3I Atlas, the porosity and the gas flow permeability. In a dense, solid object, heat transfer is dominated by conduction. The heat slowly moves from one molecule to the next, but in a highly porous medium, like 3I Atlas, the heat transfer is fundamentally different. The voids are filled with sublimated gas, mostly text, CO2 vapor. This gas is constantly moving, flowing from the warmer, deeper layers to the colder, surface layers where it escapes. This is convective heat transfer, and it is orders of magnitude more efficient than conduction. My model showed that if I assumed a low porosity, say 30%, the heat would not penetrate deep enough to activate the text CO2 at the rate we observed. The activity would be confined to a very thin surface layer, and it would quickly shut down as the surface volatiles were depleted. The observed sustained activity of 3I Atlas, which lasted for months as it approached the sun, could only be reproduced in the model when I increased the porosity parameter to over 65%. At this extreme porosity, the nucleus behaves less like a solid and more like a fluidized bed of dust and ice. The gas pressure from the sublimating text CO2 is so high that it actually lifts and separates the solid particles, creating a highly permeable medium. This high permeability allows the gas to flow freely, carrying the heat deep into the interior. The nucleus is essentially a giant, self-regulating heat engine. The heat flows in, the text CO2 sublimates, the gas flows out, and the outflowing gas carries the heat away, preventing the interior from overheating. This thermal behavior is the most compelling evidence for the hollow nature. The comet is not just porous, it is actively porous, using its internal void space to regulate its temperature and sustain its activity. The telescope data, particularly the long-term monitoring of the comet's brightness, is the input that constrains this model. The fact that the brightness curve was so smooth and sustained, without the sudden, sharp drops that would indicate a surface crust forming and shutting down the activity, is a direct signature of this deep-seated, porosity-driven outgassing. Furthermore, the thermal model allows me to estimate the age of the comet's surface. The surface layer, exposed to the sun, has been depleted of its most volatile ices. This depleted layer forms a kind of mantle, a low-density, dusty crust. The thickness of this crust is a function of the comet's thermal history. For 3I Atlas, the model suggests a relatively thin crust, perhaps only a few meters thick. This is consistent with its interstellar origin. It has only been exposed to the sun's heat for a brief period, unlike our solar system's comets, which have made countless passes and developed thick, refractory crusts. The thin crust means that the pristine, volatile-rich interior, the hollow part, is close to the surface, making the cryovolcanic eruptions more frequent and violent. I also want to address the potential for a non-uniform density distribution, which is a key aspect of the hollow section concept. While the bulk density is $0.5, text GCM.3, it is highly unlikely that the density is uniform throughout the nucleus. The cryovolcanic jets suggest localized regions of high pressure and low structural integrity. I hypothesize that the nucleus is a density stratified body. The deepest interior, perhaps the original seed of the comet, might be slightly more compacted, with a density closer to $0.8, text-GCM-3. The outer layers, which have been repeatedly fractured and redeposited by the outgassing, would be the most porous, with densities as low as $0.3, text-GCM-3. The hollow section is therefore not a single empty space, but a gradient of extreme porosity, with the most void-filled regions concentrated near the surface, where the outgassing is most active. The high-resolution images from the Hubble Space Telescope, which I mentioned earlier, show subtle variations in the albedo across the nucleus. These variations are not just due to dust deposits, they are likely due to the exposure of different density layers. When a cryovolcanic eruption occurs, it excavates material from the deeper, slightly denser layers, exposing them to the sunday. This creates a temporary bright spot, which then fades as the material is depleted or covered by a new layer of dust. The constant, dynamic change in the surface features is a visual confirmation of the internal, hollow structure's instability. My current work is focused on creating a three-dimensional model of this density stratification. I am using a technique called tomography, which is similar to a medical CT scan, but instead of X-rays, I am using the non-gravitational acceleration data and the jet locations. By precisely modeling the momentum transfer from each jet, I can infer the density and mass of the material beneath the vent. The preliminary results are fascinating. They suggest a highly asymmetric mass distribution, with one side of the nucleus being significantly less dense, more hollow than the other. This asymmetry is likely the result of the comet's long-term exposure to the interstellar radiation field, which would have preferentially heated and depleted one side of the nucleus over billions of years. The journey of 3I Atlas is a story of cosmic survival. It formed in a distant star system, was ejected into the cold, dark interstellar medium, and traveled for billions of years before stumbling into our solar system. The fact that it retained its extreme porosity and its supervolatiles is a miracle of physics. It is a testament to the incredible insulating power of a vacuum-filled, macroporous structure. The hollow section is not a flaw, it is the key to its survival. It is the reason we have this pristine sample of alien chemistry to study. I feel a deep connection to this object, a sense of awe at the vastness of time and space it has traversed. My work is to be its final chronicler, to translate its silent journey into a language that can be understood by all. The data is the truth, and the truth is that 3I Atlas is a giant, fragile, porous, and utterly unique messenger from the stars. I will continue to watch it until it is a faint smudge no more, knowing that the secrets it has revealed have fundamentally changed my understanding of the universe. The work is never truly finished, only paused until the next interstellar visitor arrives. But for now, 3I Atlas holds my complete attention, a beautiful, fragile, hollow wonder. I must also consider the philosophical implications of the hollow structure. The extreme low density challenges the very definition of a solid body in space. Is 3I Atlas truly a single object, or is it a transient aggregation of loosely bound particles? My models suggest that the gravitational binding energy of the nucleus is only slightly greater than the kinetic energy of the gas flow during the most intense outgassing events. This means that the comet is constantly on the verge of complete disintegration. The internal gas pressure is almost strong enough to overcome the self-gravity of the nucleus. This precarious balance is what makes the study of 3I Atlas so compelling. It is a real-time experiment in cometary breakup. The faint, broad tail of dust, which I mentioned earlier, is not just a stream of fine particles. It is a continuous shedding of the nucleus's mass, a slow, inevitable disintegration driven by the internal pressure of the sublimating CO2. The hollow section is, in effect, the comet's death warrant, a structural weakness that is being exploited by the sun's heat. I have been working on a new simulation that models the long-term fate of 3I Atlas. Assuming it continues to outgas at the observed rate, and assuming the current density and porosity, the model predicts that the comet will completely disintegrate within a few hundred orbits of its home star if it were a periodic comet. Since it is an interstellar object, its fate is different. It will leave our solar system, but the internal erosion will continue, albeit at a much slower rate, driven by the faint heating of the interstellar medium. The porous structure will eventually collapse, and the comet will disperse into a cloud of dust and gas, becoming a permanent part of the interstellar medium. The telescope data, therefore, is not just a snapshot of a hollow object, it is a record of a cosmic process of decay. I am watching the final, brilliant moments of a structure that has survived for billions of years. This perspective adds a layer of melancholy to my work. I am documenting the end of a long journey. The final piece of the puzzle I want to discuss is the link between 3I Atlas and Oumuamua. The non-gravitational acceleration of Oumuamua was the initial mystery that led to the more exotic interpretations. Oumuamua had no visible coma or tail, yet it was being pushed. The leading natural explanation for Oumuamua's acceleration is also outgassing, but of a volatile that is invisible to our telescopes, such as pure $text H, $2 or $text N2 ice, which would sublimate without producing a visible dust coma. 3I Atlas, with its visible $text CO2 coma, provides a crucial counterpoint. It shows that non-gravitational acceleration can be a perfectly natural cometary phenomenon, driven by the sublimation of known volatiles. The fact that both interstellar objects exhibit this acceleration suggests that it is a common feature of objects ejected from other star systems. The difference is that 3I Atlas is large enough and active enough for us to see the mechanism in action. The hollow structure of 3I Atlas is the key to understanding both objects. If 3I Atlas is a macroporous body with a density of $0.5 CS text G cm $3, then Oumuamua, if it was also a porous body, could have been much smaller than initially estimated, or its porosity could have been even more extreme. The data from 3I Atlas is now being used to refine the models for Oumuamua, providing a natural, cometary explanation for its mysterious acceleration. I believe that the hollow section of 3I Atlas is the most important discovery we have made about interstellar objects since their initial detection. It is the physical mechanism that links the chemical composition to the orbital dynamics. It is the structural feature that explains the fragility, the sustained activity, and the complex jet structure. It is the scientific truth that underlies the sensational headline. My work is to ensure that this truth, in all its complexity and beauty, is understood. The universe is full of wonders, and sometimes the most profound secrets are hidden in the most fragile, hollow structures. I will continue to dedicate my time to this pursuit, to the quiet, relentless work of deciphering the messages carried by these cosmic travelers.